Okay, I'm going to begin chapter 7 now. In chapter 6, we looked at just the basics about the trig functions. We looked at some basic angle calculations along with the graphs of the 6 trig functions along with some of the basic properties. In chapter 7, we want to build on all that, and we're going to talk about several different things in the chapter, but the idea is that we're going to build on what we've already learned there with the basics. Okay, 7.1 and 7.2 are all about the inverse trig functions. So if I have, now I've got pass out an inverse trig functions worksheet. I have this sheet, I'll talk about that in just a moment, but if I have the equation y equals sine x and I want to compute the inverse, it's all about switching x and y, right? So x equals sine y would be the inverse of y equals sine x. Now, x equals sine y means that y equals sine inverse of x, or y equal arc sine of x is another notation that you'll see in a lot of math books for representing inverse notation, okay, with the like inverse sine notation in this case. Now, I have a handout here that is also attached on Blackboard there. And on this sheet, I've got the graphs of these 6 inverse trig functions. I've got the name of the inverse trig function along with the graph and then the domain and the range. Okay, a couple things here. So first of all, I want us to observe that how we are getting the graph is just by simply switching x and y from the graphs that we've already looked at in chapter 6. Okay, so getting these curves really isn't going to be a difficult thing. Like, I know the sine curve oscillates between 1 and negative 1. Same thing with the cosine curve oscillating between 1 and negative 1. Okay, now if I switch x and y, instead of the sine curve oscillating between 1 and negative 1, I'm going to have an oscillating thing between 1 and negative 1, but on the y-axis now. Okay. Remember that a function along with its inverse on the same graph are always going to be symmetric to the line y equal x. That will always happen. Okay, so one way to see where I got this graph from is I started with the sine curve and I just rotated that graph about the line y equals x. That's actually how I'm getting all these graphs. I'm starting with the graph that we've already looked at, you know, in the last chapter, and I'm rotating that graph about the line y equal x. Okay, now on these first 2 graphs, you may notice that I've got some of the graph is solid and some of it is dotted. The reason is because we're working with a function. What do we know about a function? It's got to pass the vertical line test. So, of course, if I know if I have a curve oscillating between 1 and negative 1 on the y-axis there, it's going to fail the vertical line test. So there is a condition here on the input and output values in order to make this a function. The domain and the range are given, okay, and same deal with the cosine inverse curve. Okay, it's got to be a function, and so I'm only looking at the solid part of the graph there in order to make it so I've got something with they're going to pass the vertical line test. Okay, now the dotted lines on these other 4 graphs are representing asymptotes, okay, except in, like, I guess these 2 conditions here we're still describing a function, but there are asymptotes on the graphs. Now, I mentioned in chapter 6 that I would like you to know the graphs of all 6 of the trig functions. They are super important. You will do lots and lots of things with the graphs of the 6 trig functions in calculus. And so with that said, I feel like it is very important to know the graphs of the inverse trig functions. Again, it's no mystery where we're getting these. If we know the original graphs, all we're doing is we're just simply switching x and y, and so we're rotating that original graph about the line y equal x to get the inverse graph. Okay, the range of each inverse function is going to be important for the calculations that we'll be doing in this section. You'll see me referring to the range quite often, actually. Okay, so let's maybe take a look at some examples here. I want to find the exact value. More specifically, we're going to do this without a calculator. Okay, And so I suppose I want to know the exact value of sine inverse of 1/2. Well, I'm going to call that y, and I've got to find y since y represents the value of sine inverse of 1/2. Now, y equals sine inverse of x means that x is equal to sine of y. Okay, this is an if and only if, so of course I can read it beginning to end or end to beginning, and both would be true here. So y equals sine inverse of 1/2 means that sine of y is equal to 1/2. Now, this would be for y values that are ranging between negative pi over 2 and pi over 2. How I'm getting that is by looking at the range of the sine inverse function, okay, that is given to me. Now, that's important because knowing the conditions on y here, and I've got to find y, means that I know where to draw my triangle, okay? Y ranging between negative pi over 2 and pi over 2 means that when I draw this triangle, it's going to be either in quadrant 1 or quadrant 4. Now I can rule out quadrant 4 because sine of an angle is opposite over hypotenuse, and both those numbers are positive. If I'm in quadrant 4, of course, the opposite side would be a negative. So when I draw this triangle here, 1 is going to go on the opposite side, 2 is the hypotenuse. The leftover adjacent side then would be root 3, and of course this is one of our common triangles, right? This is a 30, 60, 90 right triangle. And so I would recognize that I'm working with a 30-degree angle, or pi over 6 would be the value in radian measure. By the way, for the problems in this section, I believe most, if not all of them, are going to be values where you're going to want to give the answers in radian measure, okay? So keep that in mind. Now, in this picture, I've drawn this triangle here, and I've also got that flipped over into quadrant 2. Sine of 5 pi over 6 would also be 1/2, right? Because it's 1 is the opposite side, 2 is the hypotenuse. So why isn't 5 pi over 6 also an answer? Well, it's not going to be an answer because 5 pi over 6 is not in the interval negative pi over 2 to pi over 2. So again, the conditions on y are important here because they tell me that I can rule out quadrant 2 and quadrant 3 immediately. Of course, I can rule out quadrant 4 because the opposite side was not a negative. You're only going to have one value when you compute an inverse because you're working with a function, and we know that for each input there's only one output, right? There's not several different outputs for the same input, otherwise it wouldn't be a function. Okay, let's take a look at part B. I want to know the exact value of sine inverse of negative root 3 over 2. Well, if I call that y equals sine inverse of negative root 3 over 2 means that sine of y would be equal to negative root 3 over 2. And this would be for values of y that are ranging between negative pi over 2 and pi over 2. Again, I always just write down the condition on y just so I know where I'm drawing this triangle here. I can immediately rule out quadrant 2 and quadrant 3. Now the opposite side is a negative here in this problem. The hypotenuse is always a positive, right, because that's the radius of the circle. So with the opposite side being a negative, I know I'm going to be drawing this triangle in quadrant 4. The opposite side is negative root 3. The hypotenuse is 2. That's going to force the leftover adjacent side to be 1. And I'm working with a 30, 60, 90 right triangle again. In this case, it's going to be in quadrant 4, 60-degree angle there in quadrant 4. And so negative pi over 3 would be my answer in radian measure. Now, 5 pi over 3 is the same radial line as negative pi over 3. So why wouldn't I just write 5 pi over 3? Like, why would I make this a negative? Well, it's because of my conditions on y. You see, I don't want to write 5 pi over 3 since 5 pi over 3 is not between negative pi over 2 and pi over 2. I would have a wrong answer there. Even though I'm talking about the same radial line, it's actually a wrong answer. Okay, so again, the conditions on y, or the range of the function, is super important to us. We need to pay attention to those conditions on y here for all these problems. Part C, I want to compute the value of cosine inverse of 1 over root 2. So I'm going to call that y. And y equal cosine inverse of 1 over root 2 means that cosine of y is equal to 1 over root 2. Now the range of the cosine inverse curve is 0 to pi. Okay, and so when I draw my triangle here, it's going to be in quadrant 1 or quadrant 2. Adjacent over hypotenuse, the adjacent side is a positive, so I know I'm going to be in quadrant 1. The adjacent side would be a negative if you're in quadrant 2, and that's not the case here. So the adjacent side is 1. The hypotenuse is root 2. The opposite side is also going to be 1 then. And this is, again, one of our common triangles. It would be a 45, 45, 90 right triangle. And 45-degree angle in radian measure would be pi over 4. Pi over 4 is between 0 and pi, so cosine inverse of 1 over root 2 would be equal to pi over 4. Okay, here's another one. Tangent inverse of root 3. We'll call that y. Y equal tangent inverse of root 3 means that tangent of y is equal to root 3. You'd want to look at this as root 3 over 1, since tangent of an angle is opposite over adjacent. Okay, the opposite side is root 3, the adjacent side is 1, and you're going to be in quadrant 1. The hypotenuse is 2. The conditions on y for the tangent inverse curve is y is ranging from negative pi over 2 to pi over 2. Okay, so I know right away when I draw this triangle here, it's going to be in quadrant 1 or quadrant 4. We've ruled out quadrant 4 since the opposite and adjacent sides are not negative here. Neither one is negative. You're working with a 30, 60, 90 right triangle. This would be a 60-degree angle, or pi over 3. So tangent inverse of root 3, that would be equal to pi over 3. By the way, I mentioned that the graphs of the inverse functions are important to know. I would strongly emphasize knowing the graphs of y equals sine inverse of x, y equal cosine inverse of x, and y equal tangent inverse of x. Especially y equal tangent inverse of x. You'll do lots of things with that in Calc 2. A little bit with that at the end of Calc 1, okay, but they don't really beat you up with it. But I would say, at least these three are ones that you want to know the graphs of and the basic information for. Okay, you will be using them, like I said. Let's look at part E. Tangent inverse of negative 1. We'll call that y. Y equal tangent inverse of negative 1 means that tangent of y is negative 1. And the range of the tangent inverse curve is for y values that are ranging between negative pi over 2 and pi over 2. And of course I can see that from the picture, right? On this graph I've got two horizontal asymptotes and the curve is between those two boundaries. Of course they're boundaries, so the curve is going to be approaching those boundaries, but it'll never get there. Okay. So this triangle is going to be either in quadrant 1 or quadrant 4 when I draw this. Tangent of an angle is opposite over adjacent. So I'd want to think of negative 1 as negative 1 over 1. You could also think of negative 1 as 1 over negative 1, right? But I don't want to think of negative 1 as 1 over negative 1 because the adjacent side would be a negative then, and that's going to mean that you'll be in quadrant 3 or quadrant 4, which we've already said we're not going to be in quadrant 3 or quadrant 4. The triangle is going to be in quadrant 1 or quadrant 2. So negative 1 is the same as negative 1 over 1. The opposite side is negative 1. The adjacent side is 1, and the hypotenuse then would be root 2. You have a 45, 45, 90 right triangle. This is in quadrant 4. Negative pi over 4 would be my answer. Okay, now negative pi over 4 would be the same radial line as 7 pi over 4, but I wouldn't want to write 7 pi over 4 because then I'm outside of the conditions on y. That would actually be a wrong answer then. Okay, so be careful about that, giving an answer that's not on the interval that is represented there for the condition on y. I do see that here and there. You want to be careful with that. Okay, and I'll stop the video here, and we'll do some more on the next one.